Welcome to the Cosmic Pie Podcast, Season 3, Episode 7. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus at the University of North Dakota here in Grand Forks, North Dakota. Throughout the podcast, if you'd like to send us any questions or comments, feel free to use our chat feature, which is running now.
Yep.
In fact, if you're out there, give us a little shout. Check it out. See if it works.
See if it works. We don't know until you do.
Now, as a disclaimer, anything that Robert and I say are just our own personal opinions, not necessarily that opinions of anyone else or any other affiliation, any institutions or any governments, any planets, any solar systems, any galaxies in the known universe.
Yep, just us. We're the ones on the hook for it.
Does that cover everything, Robert?
I think that covered everything.
Okay.
And we're in, we're at the University of North Dakota where we're undergoing the great melt.
Finally, I always say finally because it's nice when the warm weather comes, especially in February.
February, wow.
I'm just wondering what's going to hit us in a few weeks.
Right.
We're going to end for like a 2 feet of snowstorm or something, right in the end of March.
I don't know. I'm seeing next Monday 50s in the forecast.
Yeah.
So, yeah.
We'll see.
It's not being very North Dakota.
Should I sharpen the blade to my lawnmower yet? What
Probably
do
not.
Not
I'd
yet?
hold off. I'd hold off a little longer.
That would jinx it. So if we get a terrible snowstorm, it's my fault the day after, right?
Right.
Or something like that. Okay. Now, it's been a while since we were just you and I.
Mm-hmm.
So today we're going to update some news items that we've talked about in the past and also show some new things that are going on in astronomy and astrophysics and physics in general.
Yep.
So if you want to start maybe with our first item.
Okay. So our first item is on SPHEREx.
Yes.
An update on it.
So this is a big week, believe it or not, for space launches. So on Friday, the last day of the month, at approximately at least 9:15 p.m. Eastern Standard Time, and of course these things can be delayed, so kind of keep an eye out for the news. We have the launch of SPHEREx, which is something we had talked about. It's one of these telescopes that are going in space that will do a sort of all-sky imaging, in some sense, at infrared wavelengths of the universe around us. So it's a relatively small diameter telescope, only about 20 centimeters, so 0.2 meters. A very large field of view, and this is something that caught our attention when we first talked about this a few weeks back. 3.5 by 11 degrees.
That's huge.
It is huge.
I keep saying that, but
yeah, it's a good comparison. Think of the full moon, where the moon itself is a half a degree across. So in a area or patch on the sky 1 degree by 1 degree, you would put 4 moons. Mm-hmm. So that's 1 square degree. So this is 3.5 times 11. So if you multiply, so a little over 35 square degrees is the area.
So it's 7 moons by 22 moons.
Well, so you think of 35 times 4,
right?
Yeah. So, and of course there's space in between there, so you can actually hold a little bit more than 4 full moons there. But anyway, so this is a large field of, and that's only one image, right?
Right.
That's not like taking a bunch of images and mosaic them together like a jigsaw puzzle. This is one single exposure is that wide. So you could easily cover the whole sky rapidly.
Now, I've got one thing that come up. They keep talking about another major planet being out in the Kuiper Belt or beyond. And would this put that to rest or confirm it?
This will, it will never put it to rest.
Fair.
But what it'll do, it'll be able to observe certain parameter regions, that is, certain properties that a planet would have in terms of its size and its albedo, that is the amount of light that it reflects, and that would be related to the composition. So let's say an ice-covered world will reflect more light than one that's covered in dirt.
Right.
That kind of thing. And so this will, if you like, fill in some of that parameter space, as we say, observe some of those range of properties, that if we don't find anything, you can't rule it out that there's nothing there. You can just say that it doesn't have the properties of the certain range because it would have been detectable by the instrument.
I'm just thinking with it being in the infrared, if it's a gas or ice giant like Neptune, Uranus, or say Jupiter or Saturn, a gas or an ice giant, it definitely would rule them out because they would be glowing in infrared like a star. at that close.
100%. And the other thing is we've had infrared space telescopes. In fact, the James Webb is an infrared telescope.
Right.
But it does targeted observing. It's not designed to do an all-sky survey. It would take a long, long time for that to occur.
Right.
But we had telescopes that NASA have used, the WISE mission, and that has looked over the whole sky at infrared wavelengths. And it's found a lot of things, cool things like asteroids and other stuff as well. But it could have found a Planet X type of thing.
Right.
But it didn't.
So we've narrowed down that parameter space.
Exactly. So
Okay.
it was hidden from that telescope in a sense. It wasn't bright enough at the infrared wavelengths and sensitivity that it could observe at.
Right.
So that's the thing, and you can't rule anything out, I should say. You can just say, okay, it doesn't have the properties that we would be able to detect this object given the instrument that we have. So you just design better instruments that are more sensitive. Maybe they're more sensitive at longer wavelengths, these kind of things. So eventually you get to the point where, okay, if it's like any planet that we know of and it's gravitationally bound to our sun, we would have found it.
Right.
Once we reach that point, then we're done.
There you go.
Right? Because if it's even further away, we wouldn't be gravitationally bound to our sun. It would be like sort of in its own orbit around the center of the Milky Way, or on the fringe of the closest stars to our sun. Approximately the Alpha Centauri system, about 4 light years away. So there's clearly limits on how far out a planet can be and still be able to orbit our sun.
Well, there's limits on, they're saying it's there based on the gravitational effects on the Kuiper Belt objects. So there's a limit on how far out it could be, or else it would have no effect on them.
Yeah, that's been going around for several years, well over a decade now. And people are looking at all the different data sets they can get their hands on, looking for the presence of a new planet around our sun. If you go beyond the Kuiper Belt, that's kind of, and depending on how you think about it, that's intersolar system in the sense that it's just beyond the orbit of Pluto. And if you compare that, I mean by intersolar system, because if you compare it to like the Oort cloud, which is way beyond the Kuiper Belt.
Right.
The Kuiper Belt would definitely be intersolar system compared to the Oort cloud. And we don't have a good handle on the Oort cloud, what's out there, what's the population of objects that are in orbit and those far distant reaches of the sun. And if we could analyze those, that may be a better probe of a planet that could be, that has a very elongated type of orbit.
Yes.
Because you can hide something by having it orbit not in a near circular orbit, but in a really long elliptical cigar-shaped orbit, so that only part of the time it spends in the inner part of the solar system, maybe disturbing comets in the Kuiper Belt or other objects. But then most of the time it's spent way, way far away from the sun.
Yeah.
In fact, so far it'd be so faint that we just wouldn't be able to see it given our present technology.
No, I'll go along with that. Yeah. Because, for those that don't know, the Oort cloud is a spherical distribution of asteroids, comets, things like that, that's proposed to be about a light year away.
Yeah, think of it as like the leftover debris of the formation of our solar system in some sense. The crumbs that are left
That are left over, and the sun didn't have quite enough oomph to push them all the way out.
And we don't, there's a lot of talk about what actually happened in the early solar system. Since we first started finding planets around other suns, there's big talk about what we call planet migration.
Right.
That the early planets, when they formed, they move around in that sort of pre-solar nebula in the disk due to various gravitational interaction with the disk material itself and with other planets and of course the sun. And so, and a lot of simulations that have been done shows that planets actually are almost like a train where they go into the sun. They migrate inwards. And the idea is, well, if these planets are formed from not primordial material would be, if you think of normal elements, hydrogen to helium in the periodic table. Anything that is more than that, for example, carbon, nitrogen, oxygen, so on and so forth, those have been manufactured or formed inside of a pre-existing generation of stars. So you build up what we call the metallicity of gas over time.
Right.
So planets then would have these metals, like Earth has iron and carbon and so on. That wasn't formed in the beginning of the universe. That had to be formed inside of stars. So what these planets do when they migrate, as they move into the outer atmosphere of its host star, they contaminate that material. So if the host star was made with material that had less metals in it, so closer to being primordial, if you want to think of it that way, then the planets could, contaminate that with metals.
Right.
And so you look for stars that have this high metal content as maybe being recipients
Of a train of planets.
of a train of planets.
Yep. And it would be, because it wouldn't be smooth, you would actually see that was the evidence of that. There are different ways and reasons why you would see, hey, this star has been contaminated. We've seen that. So
The only problem there, of course, is that the host stars form from that material in which the planets form from.
Right.
So what is the differentiation? In other words, what is the metallicity difference between those forming planets and the star itself?
Yeah.
If they have very similar compositions, then it'd be very hard to see the difference.
then it would be hard. Yes.
Yeah.
And there we go. We're back. But, it's like a Jupiter would be visible in the sun spectra if it ate Jupiter, because of the various contaminants that would come, the higher carbon and things like that.
Well, here's the thing to think about. And of course, it would be very unusual if it happened when you're observing. But imagine that you would all of a sudden you see the presence of strong lines of methane in the atmosphere of some star that wasn't there before.
Yeah, that wouldn't last very long, but that would be,
Because
it
it's
ate a
swallowed a
planet.
gas giant. And if you
Right.
look at enough of these stars, if they're early on, of course,
Yeah.
the statistics of that goes against you quite rapidly when you figure out the numbers.
Right.
It'd be cool to see, but I mean, the chance of that happening is very, very tiny.
Right. And you'd probably see it more on an M dwarf, because they at least can support molecules. Nothing like methane for very long, but we see titanium oxide, for instance, in there.
Yeah, so those molecules would survive, in other words, in that outer atmosphere of that host
Right.
star. It's not hot enough to disassociate, break those molecules apart due to mainly collisions with other
Yep.
particles, atoms, and stuff in the atmosphere. Now, the other thing happening this week is we have the 8th launch of the Starship. So this is now scheduled for 5:30 p.m. Central Standard Time on this Friday. So just late enough in the day I should be able to tune into this. Now, in some sense, it's a reflight of the flight number 7, which, as you might have found out a few weeks back, it was catastrophic
Yeah.
in the sense that the upper stage exploded. So it wasn't able to do all of its engineering tasks assigned to it, including the nice reentry that we always seem to know and love now as it was coming back. And you see it glowing really bright pinkish reddish colors, right? As it's
Right.
to land in usually in the Indian Ocean somewhere. So this is kind of a reflight of that. So it's the upper stage is again a new design of the Starship itself. So it's
Okay.
like because they redesigned it for the last flight, but really didn't get a chance to test it
test
out.
it. Yeah, right.
So they're going to test it this time. So hopefully it works. Whatever was wrong last time, hopefully they fixed it. And it's going to launch, if I'm not mistaken, like a microsatellite in the process as well.
Okay.
So there's all kinds, a whole slew of engineering tasks that it's going to perform. But but all of this is really predicated on the fact that SpaceX as well as Blue Origin have been assigned contracts to develop the lunar lander.
Right.
So we have the SLS, the Artemis project, right? The Saturn V-like spacecraft, for those who remember the Apollo program, that's going to take men back to the moon and do a landing in, first of all, in the South Pole region.
Right.
That requires a lander, obviously, to go from lunar orbit down to the surface and then back up again to lunar orbit. But that is not ready to go. SpaceX is hoping that Starship is going to be the one to do it for them. And
Okay.
of course, Blue Origin has developed independently their own lander.
Right. I forget what its name is, but
I mean, they showed up like a prototype design a couple of years back.
Yeah.
So, and they're I find them less open than SpaceX.
right.
Blue Origin seems to keep things under wraps, and you don't really know what's going on until they're ready to open up and present the finished product.
The
to
finished
world.
product. Yeah. I'm just glad to see they're back in the running. They went through a bad patch there for a while.
Yeah, I mean, they did launch New Glenn recently,
Mm-hmm.
so that's that was well received. That was very successful,
Right.
considering that it was its first launch. I've heard a lot of rumors about leadership in Blue
Right.
Origin, that they had some trouble with that, and Jeff Bezos at one point had to step in and give early retirement to some people
Right.
to get things going back in shape again. So whatever it is, and who knows? Probably we don't know the true story, what actually happened, anyways, because it's a non-public company. These
Right.
people are not both SpaceX and Blue Origin are not open on the stock market. You can buy stocks from them. They're not a publicly traded
Okay.
company.
Which means they're not obligated to put anything out
Yeah, they
there.
don't have to tell their shareholders anything, right?
Right.
So, and that would be public information, obviously. So, yeah, so maybe that's the good way to do things, to develop that technology. But we'll see what happens. But it's interesting, in the last federal administration in the U.S., the Biden administration, Starship, so Elon Musk, which is in the news for a lot of different things lately, so we won't get into that. But Elon Musk has criticized the FAA for not approving launch license in time, that they were, he claimed, dragging their feet as if you like, payback from the Biden administration,
Right.
and that they could have launched a lot more Starships than what they have up to this point. And they need to launch them because they need to prove out the technology to incorporate that in a lunar lander.
Right.
And if you don't have the lunar lander in time, then the whole Artemis project gets delayed. In fact, we know the next flight, and that's been delayed, is going to just have astronauts going around the moon, sort of like Apollo 8 redo in that sense. But, you know, you're proving the new spacecraft and everything, right? And if I remember the first launch, and there's only been one with the SLS, that didn't even have all the environmental systems on board.
Oh, wow.
So it's not like it was like a complete prototype and shakedown of every system that you need to support human life. That was not the case.
Okay.
And so there's been a lot of and so you're never going to land on the moon unless you have a lander, obviously.
Right.
So things need to kind of pick up the pace a little bit with the Starship type of stuff. So we'll see how that plays out. But we talked about this in the past. There's also, once again, rumors. So you take rumors as far as what rumors are, that the Trump administration is looking at potentially shaking up the whole Artemis project. So the Space Launch System, the main rocket, that whole rocket launch costs on the order of $4.2 billion a launch.
Right. Which seems a bit excessive.
And it takes roughly 2 years to put it together to launch it.
That seems a bit excessive.
So that, you know, there's a lot of issue there, especially now in this environment of saving as much money as possible. Could you do better by getting rid of, and people always call it, some people call it the Senate launch system, because the administration at the time, I think it was the Obama administration, but I might be wrong with that, they wanted to do away with that rocket.
Right.
But the senators, the Congress, pushed it, and they control the purse strings.
Right.
They actually gave more money to NASA than what the president requested at the time, saying, no, take this money. I want you to develop this system. We want to use this. Now, there's obviously going to be a lot of politics mixed up in all of this. So that aside, just by looking at the raw numbers, is it better to have an SLS type of system that, let's say, is $4.2 billion a launch and takes 2 years from start to finish to launch it? Or would it be better in terms of money and time frame to put together a few, like maybe, the Falcon Heavy vehicles, which cost somewhere around $150 million a launch?
Right.
Instead of launching one rocket, launch maybe 2 or 3 of these rockets, rendezvous in Earth orbit, send the spacecraft on the way to the moon that way.
Right.
Or some
Something
configuration like
that.
Would that, in the long run, be a lot cheaper and a lot faster? My vision, my vision is always to put like an Antarctic type of base on the moon, and make it like Antarctica. Nobody owns it,
Right.
and that you could have it like international partners in the project. So just a place where we do science and practice engineering and working on the surface of the moon, ultimately allowing us to do that stepping stone to Mars. Now, if somebody comes along and says we should forget about the moon, let's just go to Mars. That'll get everybody excited. Yeah, it will. And we go there and we land on Mars and then we come back. Is that it?
Right.
You see?
Well, that's what happened with the moon.
Yeah,
so.
and I'm thinking the long range type of thing maybe is the better approach. You could still go to Mars rapidly just to keep the excitement going and give people, young people motivation and inspiration of why they should go into all these different fields that support going to Mars and living there, and beyond what happens, in the distant future with the rest of our solar system.
Right.
But in the process, bring a base on the moon and stay there, and have that base like the International Space Station there for year after year after year, where we send crews up and replace them, normal sort of periodic crew rotation that happens, sending up supplies, maybe bringing stuff back from the moon,
Right.
all this kind of stuff. Things kind of would be a little cheaper maybe nowadays. You could send up material and then 3D print whatever you need on the moon, rather than sending up the object itself.
I mean,
who knows?
The moon is metal poor, meaning not astronomy metals, but actual metals. It is known to be metal poor. So not a lot of iron or anything or things like that you can get at, but there is a lot of aluminum and silicon caught up in the rock.
Right.
So, and potassium and a few other things. But
so what you need then in terms of ingredients, you bring it from Earth, and what you don't need can get in situ right at the moon itself. You would use that material.
And let's face it, people talking about oxygen on the moon coming from water. There's oxygen. I mean, rock is primarily SiO2. But we need an efficient energy conserving method of stripping off the oxygen from the silicon. And that would be a great place to test it, is on the moon.
We're at sort of a time where you could say that in 50 years from now, people are going to look back in this year, in 2025, and say that the decisions that we make now had a long-range impact in terms of space exploration.
Yes.
And I think we're almost at that turning point now. So we'll see what the Trump administration decides to do in terms of where their support lies for going back to the moon. So,
Okay.
yeah.
And Bill has a question for us, Bill Schwalm. Regarding a base on the moon, considering the problem with moon dust, regolith, wouldn't it be better to have a station in orbit around the moon? And there is some talk about that.
Actually, that is being done. It's called Gateway.
Oh, okay.
Yeah, so I just seen an article that was published yesterday about part of the Gateway modules being put into a clean room. So they're actually building this, and the idea is to put a station, a space station in lunar orbit, so that you can transfer back and forth
Okay.
to help resupply. A lot of people don't like that. They like it going, just get to the moon surface. Let's get going. Don't hesitate and waste all this money by having a space station in orbit around the moon type of thing. So there are pros and cons that you can argue. And Europeans are involved, I think, in building that gateway, at least doing a lot of it. But I'm not 100% sure on that. But I think that's one of the things they're contributing to the Artemis project.
Because Bill is correct. Moon regolith, moon rock dust is some nasty stuff. I mean, we think of it dust as being this smooth, a little gritty, but there it's like razor blades.
Yeah,
it's
I mean,
shattered glass.
There to take care of that, I would probably prefer you to have sort of a room on the base on the moon itself, which is sort of like a clean room because it's 1/6 gravity, so you can utilize that by having showers and water systems set up somehow, or even a wind system right under pressure that can blow off the dust from you and all your belongings and so on, and maybe eject that back on the surface of the moon somehow, or contain it to study it or whatever. But you could do a lot of that scrubbing, if you want to call it that, on the surface of the moon itself.
Right.
In an isolated docking hatch that goes to the main base, and not bring that stuff in the base. It's
just you don't want that stuff getting into electronics. You don't want it getting into your lungs because it'd be like asbestos.
Yeah. So it's like on what is it on Star Trek? They always go into that containment place or something to decontaminate when they land on different planets or something. So it would be de-dusting or something, right?
Right. And they just hose you down,
Yeah, with air or water or something else you could think of. Maybe even electrostatically, because dust does have electrostatic charge.
Right.
In fact, astronauts reported levitation of the dust. And it reflects the sunlight, of course. So you can see the dust levitating on the surface of the moon, which is kind of cool.
That's kind of cool.
Be like, I don't know what that, probably like a haze, like a low-lying haze or something when you're on Earth here or something. But that'd be really neat.
Yeah.
But like I said, some of the major decisions that we've made in this administration will set the stage for what's going forward. I think that's probably a correct statement to say.
I think that's a correct statement, yeah. So, moving on.
Talking about objects like asteroids.
Yeah.
So I guess Bruce Willis, we don't need him anymore.
No. It's down to a 0.005% chance of hitting Earth, so it's essentially zero. No city wasting impact in 2032.
Now I noticed that after we did a podcast describing this discovery, and the chance at that time was something around like 1.5 or something % chance of hitting the Earth.
Right.
All of a sudden, I started to see it everywhere. Everybody started jumping on the story. And the chance kept going up as you attain more observation. In fact, I think it got up to around like 2.5% roughly.
Something like that. Yeah.
Yeah, and people started to get a little worried
Yeah.
than
But-
what they were.
But
But
people forget that 2.5% is like a 1 in 48 chance. And that's how all these stories were billing it as, 1 in 48 chance of it hitting Earth. And it's like, yeah, but that's only 2.5%, folks. When you say it like that, it's like, oh, hey, that's no big deal. You say 1 in 48, and all of a sudden people's ears perk up, and they're like, oh, wait a minute.
But I know even NASA at one point had said, well, don't panic. We do have mitigation system that we can use, because we had the project that launched just a few years ago where impacted a small asteroid. And this is a small asteroid. It's not a large one, 40 to 100 meters or so in diameter. And we could actually alter the orbit of this asteroid just by hitting it with a heavy mass. Mm-hmm. That's all, right?
Or painting one side of it dark, or
Yeah.
any number of things. We could actually change it.
So if the probability would have been a lot greater, significantly,
we would have had to plan to.
we would have
test
to
these
send a mission up to do that.
Yep.
So it was the DART mission. Right? So, anyways, we don't have to worry about this guy. But
No.
this is not the only one that's out there.
Oh no.
Hundreds of thousands of these things
Right.
are out there in orbit around our sun, and some of them go through different types of gravitational perturbation effects and so on.
Yeah. And if you're interested in seeing them, we've talked about spaceweather.com because they keep monitor solar storms, coronal mass ejections, and sunspots and things like that. So an excellent site. But they also keep track of near-Earth objects, NEOs. And so if you're interested in how close and what we're being buzzed by, that's a good resource, because if you scroll down to the bottom, they list out the NEOs, when they're going to pass by, and how close they're going to get.
Yeah, and the thing that the layperson always forgets is it's not like you can do a survey of all of the asteroids in our solar system and then kind of slap your hands together and said, we're done, let's go have dinner. It doesn't work that way, because these things do change their orbit.
Right.
They rotate, they get heated on one side more than the other when this happens. There's lots of different processes that are at work here. So the orbits of these asteroids can change. And so
Right.
at some point, one can change that it will be a direct collision with the Earth.
Right.
And we better be prepared for that.
And in fact, that's why it took them so long to figure out that there's a 0.005% chance. The orbit was uncertain enough that they needed hundreds of data points instead of like the 3 that a
Yeah.
major body needs.
Yeah, the first thing you do is you go back in the past and look at images that were taken of areas of the sky where this asteroid would have been,
Right.
to see if it was captured in those images to give you some new data points type of thing. And then you watch it going forward for a period of time.
And then there's the amateurs, which I kind of have a love-hate relationship with that name, but there's some people that really know what they're doing that aren't affiliated with NASA or anybody else that look for and monitor things like this.
Yeah, you can't hide it. I mean, anybody
Yeah.
with a telescope and knows what they're doing can see it.
All right.
So any country, can calculate the orbit of this object and say, yeah, you're right, this is what we get too. In fact, you'd want to do that.
And like I said, you got people just, with enough money to buy a half-meter telescope that can sit there and they're watching for these things.
Yeah, exactly.
That's how most of them are found, as a matter of fact.
So this one we don't have to worry about, but we can't let our guard down. That's the
That's
point
the thing.
here.
Yep.
Yeah.
So,
Another update. So a couple weeks back, we had 2 landers that were sent on their way to the moon, and the Blue Ghost lander, which was the one built by Firefly Aerospace, is due. It's in orbit around the moon now, and it's due to try to land on the moon. I say try because if there's any issues, they can wait. Right? They're safely in lunar orbit.
Right.
So they can monitor the systems, wait until they know 100% sure they're ready to try this.
Right.
And go ahead. So if they need a few extra days,
and let's
why not take the time? Right?
and let's face it, the luck of landing on the moon has been pretty poor here the past few attempts. So,
Yeah, I mean, a lot of this is private companies
It
doing
is.
this work, right? So, when you do things for the first time, obviously, it can be a lot of issues. But this spacecraft is scheduled to attempt landing on March the 2nd. So
Okay.
that's coming up rapidly here.
so that'll
And
be
Maria Crisium, or the Sea of Crisis, is the landing site for the spacecraft. So we'll see how that works. So that's what, on Sunday, is it? So
Sunday,
Friday,
yeah.
Sunday. So, yeah, be very interesting.
It will. I mean, it's be nice to see one of these get down and actually start doing science. Sorry, but there it is.
Yeah, well, then the idea is if you can come up with a cost-effective lander, then universities or small colleges can put experiments on these instruments, and then can land on the moon and do various things. It's kind of cool when you think about it, right?
Yeah.
So right now, universities can do a lot of experiments in Earth orbit, so you're just extending that reach outwards, to the moon itself.
Right.
So, kind of neat.
So I hope you were ready for that one.
Yeah. So also coming up in March, speaking about the moon will be going in the shadow of the Earth. So that'll be our lunar eclipse. It's just been a while since we've had a lunar eclipse.
It's been a while since we had a full one.
Yeah. So this is going to be visible mainly from the Western Hemisphere.
Okay.
And so it's primely placed for us and anyone else in the United States, essentially. So for us, the deepest part of the eclipse, when the moon's in the darkest part of Earth's shadow, will occur from about 1:26 to 2:31 a.m. Central Daylight Time. So the thing around here, of course, what do you pray for, or anywhere else for that matter, is
clear sky,
clear enough to see it. That's what will get us, right? So it's going to happen. It's just, will we be able to see it? That's the main thing. And I like lunar eclipses from the point of view that anybody essentially on the night side of the Earth at that time can see it. So long as they have the weather to cooperate. So it's not like a solar eclipse where it happens in such a small region on the Earth that unless you go to that spot, you don't see the total eclipse of the sun. Yeah. A lunar eclipse is more widely viewable. That's why more people have seen a lunar eclipse than a total solar eclipse.
Right.
And so that'll be interesting. So hopefully, and for us, of course, March the 14th is what?
I don't know. Is that St. Patrick's Day?
Spring break.
Oh, spring break.
So all of our students will be gone that week.
Yeah.
But I have told the astronomy students that this is coming up. I mentioned in class already, and I'll advertise it again as we get closer to the spring break itself. So that's kind of neat to see that.
Excellent. Yeah. So it should be fun,
It should be.
I'm going to ask you a question.
Yeah.
Why does it turn red? Why does the moon turn red?
Yeah, so what's going on here is if the Earth itself did not have an atmosphere, the moon would be completely black, because the only way we see the moon at optical light is from reflected light from the sun.
Okay.
Now, what can happen is when the Earth has no atmosphere, there's no light that would get to the moon itself to then get reflected back to the night side of the Earth so that we could see the moon. You just see like a dark spot that would cover up stars. If you know your star field in that region, and then you have a better view, of course, with binoculars or telescope.
Right.
And what happens because the Earth has an atmosphere is some of the light that skims through our atmosphere gets bent or refracted. And it can be bent in the right way that it actually hits the surface of the moon and then gets reflected back to the Earth. Now, the refraction depends on the wavelength of light. So the blue light gets refracted or bent more than the longer wavelength light.
Okay.
And so what happens in this case is it's the longer wavelength light that is able to refract at the right angles that allow it to reach the surface of the moon behind the Earth relative to the sun.
Right.
And then get reflected back to the Earth itself so that we can see the moon. Now the color, the reddish color, sometimes it's not always red, sometimes it's really gray looking, really dark kind of color. That actually depends on what's in the atmosphere at the time.
Oh.
So if we have a lot of volcanic eruptions that happen to occur, or maybe one volcano exploded not long ago, and a lot of that volcanic dust gets kicked up into the higher atmosphere, that actually has an impact on the color of the moon during the lunar eclipse. In fact, atmospheric scientists look at the detailed measurements of the color of the moon to get an idea of what's going on in our atmosphere at that point.
Okay, I didn't know that. That's kind of cool. Okay, cool.
Yeah, so that's really interesting. But yeah, if the Earth never had an atmosphere at all, the moon would be completely dark.
Right.
Completely black during a lunar eclipse.
Okay, cool. Shall we move on?
Let's move on.
All right.
Now, this is once you get the significance of this image, this is like stunningly cool.
Yes.
This is a James Webb Space Telescope image of a star that's in the act of forming. It's called a protostar. And it's of a particular type called a Herbig-Haro 30. It's the number 30 in the catalog, or HH30 object. So George Herbig and
Guillermo Haro.
from Mexico. So Omar's been on this podcast in the past. We talked about him specifically. They put together a catalog of these weird objects that had these strange emission lines in the optical.
Okay.
And what we discovered some of these objects at least, are these star-forming stars, or stars that are newly forming, these protostars.
Right.
So the first stage of stars, an object sort of goes through when it's collapsing down to form a star, is a protostar. And eventually it turns into what we call a pre-main sequence star.
Okay.
So this is early in the formation of the star itself. But what's interesting about these type of objects is they're associated with these jets that you see launched. One goes upwards in this orientation, one is downward.
Mm-hmm. And go ahead.
No, I was going to say, and that's what catches your eye.
Yeah.
If you see this on an image, when it produces emission lines that you capture, the emission line spectra from these objects, that's what sticks out like a sore thumb to astronomers when they're looking at this object, whether it's through normal, imaging or looking at the spectrum of the object itself. So it has these unique signatures that make them unusual. And of course, that's what captures your attention. That's why you turn and say, hey, what's going on here? And you study it in detail and you find out that eventually you realize these things are protostars. The objects in the act of forming to become a star.
And the jets are due to conservation of angular momentum and magnetic fields, correct?
Yeah, the magnetic fields the magnetic field lines get twisted because the thing is rotating. Think of a disk of material, and you can see that disk. It's sort of horizontal in this image. In the very center, that you can see the dust,
right?
The absorption of the light from the disk itself. So all of that is rotating around conservation of angular momentum. Once again, if you have magnetic fields, they get twisted up, and then you get these collimated jets due to the interaction of the charged particles. And if you know it's a charged particle, so any charged particle that's accelerating, so think of one going around in a circle, is going to emit light.
Emit light, yeah.
And it's usually in these type of environments, synchrotron emission, which is radio photons.
Oh, right.
But in this case, of course, it's JWST image, so it's in the infrared. So infrared photons can be released as well.
So it's probably dust coupled with the gas, the plasma that's being injected.
And the collimated jets, like I said, those are the magnetic fields that are twisted up.
Right.
That cause that linear-like features. But what actually, this is interesting, from a point of view of fundamental physics, what actually causes a jet to form, what causes a jet to launch, what causes a jet to maintain itself, those are all questions that people are working on even today.
There we go.
There's an avenue of research that needs to be explored. So that's there. But it's interesting that we're seeing a star that's just in the act of forming.
Right. It's not even undergoing nuclear fusion yet.
No, not yet. So the heat that's coming off it is just some thermal emission, right? The fact that it has a temperature and it's getting smaller and smaller. Now, this particular object is about 477 light years away.
Nice.
And that's the latest measurement with the Gaia Data Release 3 measurements. So,
yeah, I'm trying to think of where that would put it because I'm familiar with a lot of the star-forming regions. That's a little closer than Orion, though.
Yeah, Orion's like on the order of 1,300 to 1,500 light years away. So it's a lot closer than Orion, which is good because it gives us more detail that we can look at, given the angular resolution that's limited, of course, in any instrument that we use. We can study the structure in the disk itself. And you can see there's all kinds of stuff going on here. So you study, obviously it's a color image of images taken in multiple filters put together. And you can then look at each of those filters and how bright different parts of the object are to get some idea of the underlying physics that's at play here.
Right. I mean, I'm sitting here going, which filters and which ones are colors are cooler than the others, because that's essentially what infrared is measuring, is how hot things are.
Yeah.
So,
and the dust lane is obvious. That's the dark horizontal line through the middle. So there's lots of dust there. I mean, even in the infrared, that light is being blocked by that dust.
Right. So, it's dense.
It would be nice to take like an interferometry and look at it like at radio wavelengths.
Right.
To get some more, hopefully get a much higher resolution, like the Event Horizon Telescope, to see what's going on in the very heart of these objects. That would be, and that's a lot of work.
Right.
For maybe low, it's not as sexy as looking at the shadow of black holes. But if you're a person that studies the formation of stars, it's just as important, you see? Mm-hmm. So it's all a point of view of perspective here.
And what you can get funding and time for.
Well, it'd be nice when arrays like the Event Horizon Telescope or something similar to that become available to a wider range of people.
Right.
So they can look at objects like this, or at least they accept targets like these to get these high, very, very high angular resolution images. And that would be really cool to see what's going on right in the heart of this thing. And maybe provide information about the how the jets are created, for example, and then you can use that information. So this is like a small scale, but a very large scale version of this is what we have with active galactic nuclei, which are supermassive black holes. Could be up to billions of solar masses, material going around in a disk, accretion disk like structure, and a lot of them have these jets. And the double jet, the one jet going out on the top, let's say, of the disk, and the other one going down in the opposite direction, the so-called counter jet. But how do those jets get formed? That's a very large-scale, macroscopic, huge object. So if you lower it down to something much smaller but closer,
you might get some details.
well, that's it, right?
That's it.
Yeah. So you never know what science you can get out of this object and how you ultimately apply it in that sense.
Right. So kind of cool.
Now, speaking about the James Webb Space Telescope.
Yeah.
Now, okay, so I guess, how should we say this? The James Webb Space Telescope team had been told, as far as we know, I don't know, this may or may not be true once again, but it's been published, that they are to prepare for a potential 20% budget cut.
Right.
Now, this is obviously will affect the science that comes out of the telescope itself. It's
Right.
If someone tells you cut back a 1, 2, 3, up to 5%, you're gonna feel it.
But you can
probably deal with overhead and stuff and slice things. But 20% is significant.
Right.
That's a major cut. So I don't know what happens in terms of the cut. Nothing's been decided as far as I know. That could be potentially graduate students lose jobs and positions, postdocs lose jobs.
Right.
Who
and
knows?
Science doesn't get done.
In science itself, the engineers, have to leave the project. And if something were to ever happen to James Webb, you don't have the expertise around maybe to troubleshoot like you should have.
Right.
And then you got to call in people, could you please come back? We have a problem. And what happens if they say, no, I have another job now because I got released from the project?
Right.
You don't know the potential impact. It may or may not do really anything. Science will take longer to get done, but ultimately it will get done. Now, the thing to remember about James Webb Space Telescope, it has a finite mission.
Right.
Because it depends on making sure you have enough propellant on board to point the instrument.
And enough coolant to keep the sensors cool. It's infrared. So,
yeah, well, it's passive cooling, right, with the sun shield. Yeah,
I thought it still had active coolant.
No, it's the pointing that's the major issue,
Okay.
and that's why when they first put it in the Lagrangian 2 position, the L2 position, they did so with the optimal use of propellant because of changing the orientation when you're pointing at objects. You see.
Okay.
So the fuel will run out eventually, and they said instead of having a nominal life mission of 5 years, like when it was first launched, which was that space telescope that was launched in 2021 on Christmas Day.
Right.
So it'll be 4 years this coming Christmas. So it's been a little over 3 years now. Nominal mission of 5 years. So we'd be almost getting near wrapping it up anyways. But because of their really stringent, use of the propellant, they managed to extend that lifetime they project out to 10 years in total.
Nice.
So
But maybe not after all.
Yeah, so hopefully the budget cuts won't have too much of an impact, but everything's in such a state of flux now.
Right.
No pun intended, because that's what we measure in astronomy.
But we don't know
We don't know what the impact will be, if anything. I mean, how many times have you heard governments threaten to take away money from a certain project and then people protest or get upset and then they put the money back again?
Right.
I mean, so you never know. I mean, how many, like the Europa Clipper mission, which is on its way, so you can't defund it now, but you could, I guess, get rid of the scientists so nobody listens to it anymore.
Right.
But that, that was like slated to be canceled many times.
Yes, it was.
And it got resurrected again, right? And even the New Horizon mission that flew by Pluto
Was canceled more than once.
That was canceled more than once as well. And then they redesigned the mission and brought it back. And so it takes a lot of patience if you're a principal investigator to work these projects through all of the red tape that you need to go through the government. It's unreal. I wouldn't want to do it. I just don't have that patience for that. So
right. That's why we're at the university.
Yeah, that's why we don't work for NASA, I guess, and in that kind of that task.
Hectic, high tension job. Yeah.
Yeah, because you just never know. But the other kind of cool thing is that this is an image that was released from the Euclid mission. So this is designed to observe the universe. And it was put together initially to look at enough part of the universe so you get some great measurement of the dark energy component. And one of the things about that, we know that dark energy exists. We have lots and lots of signs of that. But one of the most interesting things today is, does it change with time, the dark energy
Right.
itself?
Does it increase or decrease?
Yeah, and nobody really knows. So you're looking for time evolution. It's a harder puzzle. The uncertainties are much greater in that than just to say, okay, it's this and it represents this amount in terms of the energy matter content of the universe itself, if you want to put it in those terms. So time evolution is a real thing that's extremely interesting, put it that way. And so this mission is sort of designed to do that, but you can do a lot of other things as well.
Right.
And what you see here is a galaxy in the center of the image, NGC 6505. But if you look right near the heart of the galaxy, you see a beautiful Einstein ring.
Right.
I mean, just gorgeous. It's just unreal, right, this ring.
Very few are that complete.
So what you're observing then is light from a distant object, distant galaxy that's in the background, that when this light from that object passes near the center region of this galaxy, it gets deflected, analogous to a lens, if you ever played around with lens. And if you don't, I mean, here's an idea. Take a champagne glass, if you have one at home, tilt it up. But before you do that, make sure you empty it of champagne. You don't want to waste good champagne. And you tilt it up and then look through the bottom of the stem as you pass the stem across some light source. And as you do that, you'll see like a ring of light on the stem itself. So the glass is acting like a lens in that case, distorting the image that you see behind of the light source itself. And it's operating in basically the same way here. Of course, it's the curvature of space that's causing the light to go through different paths depending on exactly its trajectory. But it's acting like essentially like a giant lens.
Right.
And you can get information not only about the object that lies in the background. For example, a lot of times these objects are magnified. So you could actually look at the spectrum of those light blobs in the ring itself and be able to, number one, look at the different blobs. So there's roughly about 4 giant blobs that I see there. If you take the spectrum of all 4, you can compare the spectra. And if they're identical, it's the same object.
Okay.
Okay, so you know it's multiple images of that object. But the other thing is, because it acts like a magnifying glass in some sense, or a telescope, if you like, you can then take the spectrum of an object that's so far away and so faint that otherwise you'd never be able to do that with the current instrument.
You'd never see it.
But you can do it now because it's magnified enough that you can get a good signal-to-noise ratio and see the different lines in the spectra itself, absorption or emission lines. So it's quite interesting from that point of view to do that.
Yeah.
Now, this galaxy itself, by the way, NGC 6505, and if you're not familiar, NGC stands for the New General Catalog. So it's a catalog of astrophysical sources that was developed I started in the late 1800s.
Okay. I didn't know how old it was.
If I'm not mistaken, John Herschel, so William Herschel's son, was involved in doing that. And what this galaxy itself is at a distance of about 608 million light years.
Nice.
Now, if we get the spectrum of that blob of light that's in that ring, then from that spectrum we'll be able to measure the redshift of the background galaxy that's lensed and be able to tell how far away it is. So we don't know. The typical rule of thumb is they're usually double the distance away on average, but it's not exactly.
Right. It depends on the mass of the foreground galaxy.
Yeah, it depends on the alignment and everything. So that galaxy is probably at least well over 1 billion light years away, the one that's being lensed, the one that creates the ring. The one that's the light in the ring that you see, I should say.
Right.
So that's interesting from that.
Yeah.
Now, speaking about that, it's, so you look at the ring itself and you see, well, what is the curvature of space that would create that? And that curvature of space then tells you how much mass and energy is in that region of space.
Right.
So in other words, it's mostly mass. And so you get an idea of the total mass that's responsible for making this Einstein ring. Okay?
And then you can compare it to its
that
distance.
total mass is the total. It means all of the normal matter, like baryons that emit light, but it also includes dark matter as well. So you can get an estimate of what fraction of dark matter is in this foreground galaxy that's doing the lensing
Right.
by just looking at the lensed galaxy from the background.
How well it's lens. How strong is your lens?
And that's one of the ways we can put constraints on the amount of dark matter that's out there. They say there's got to be more matter than what we can see. And there's been a recent study that someone has done that just came out today, this afternoon. Now get this one, Robert.
Mm-hmm.
And I haven't prepared a slide for it because it's that new.
Okay.
Okay? But
Well, let's talk about it again.
yeah, but watching pulsars, and we can actually time pulsars, the arrival time, so you get an idea how far away pulsars are because of the accurate timing with atomic clocks and so on. And what the study did is they looked at the motion of binary pulsars to get an idea of the total mass that would lie between them that would affect their orbits, their orbital motion.
Okay.
And that includes putting constraint on not only what would be there in terms of the neutron stars themselves, but any dark matter that's there.
Okay, that's kind of neat.
And what they've come up with is an estimate of the average amount of dark matter. And what they said is that an object the size of the Earth, okay, you'd expect about 1 pound of dark matter in that volume.
Interesting. I'm surprised it's that much.
Well, then they go on to say, given that we find certain number of pounds of gold in the Earth, that makes dark matter way more valuable or priceless than gold. Well, of course, that's a silly thing, but I think they did that for the hype of the publishing the article. I mean, not in scientific journal, but in like the news, the science news articles on the web.
Because you want people to click on your article and read it. So
So next time if someone says, well, how much dark matter is out there, Robert? Well, you know what to say. Well, for a volume about the size of the Earth, it's roughly about 1 pound.
Right.
So you have something you can, makes a good talking point, in that sense.
Of course, I could make, be a stickler here and say pound is an amount of mass. So,
Yeah, well, they did make that because most people won't make that distinction, right?
Right. Most people don't.
If you take a mass and you have it on the surface of the Earth on average location,
It's going to be a pound.
G, then it's a pound, right?
All right.
That's what they're arguing here. And the other interesting thing that also came out today
Okay.
that caught my attention, once again, too close to podcast time, I didn't have a chance to prepare a slide, is that there is evidence
Okay.
that the Earth itself, which includes the solar system and the sun, passed through part of the Orion Nebula roughly 14 million years ago based on Gaia DR3 data.
Interesting.
So you take the motion of all the stars around us that the Gaia mission has produced, the parallax measurement, proper motion measurements, work back in time, and the Earth, our solar system, passed through a part of the Orion Nebula about 14 million years ago, so a high-density region.
Interesting.
And they're looking at any effect to the climate of the Earth. Now, there was something that's in geology, right? There's a certain period, I forget the name, what they call it, where there was a climatic shift. The Earth became a lot cooler at this point. Now, they don't know if there's a direct connection. They're just looking, right? A lot of times, as we say in science, just because there's a correlation
doesn't mean it's causation.
Exactly.
Right.
And that's the same kind of situation here. They're not going out on a limb and saying that this is the direct connection. But it's interesting to know.
But some news reporter, I'm sure will.
They will. That's the unfortunate part of this. But the important thing here is we always forget that, our sun is on its orbit, dragging the solar system with it, if you like, around the center of the Milky Way. And it takes about 240 million years to go around once. So we've gone around, since the formation of our Milky Way galaxy, probably about 54 times.
Okay.
And in terms of when the sun and solar system formed, probably around 18 times.
Okay.
So we've gone through regions of space, local, that have been of lower density and higher density. And we also go up and down through the plane of the solar system's disk.
Right.
And one sort of cycle takes on the average about 80-some million years for it to occur. So we're going up and down, as well as in our orbit going around the center of the galaxy. So we've got this sort of oscillation, if you like. And so it's not surprising, it's not unexpected that there will be periods of time in the past, not that long ago, geologically speaking, where we're going to be in a sort of a new environment around us compared to where we are today.
Right.
And so if you're going through part of the Orion Nebula, which is, 1,300 to 1,500 light years away, there is depth to the Orion Nebula. So there's no, what would you say is the distance of the Orion Nebula? It's like saying, what's the distance to Grand Forks if you're like one mile outside the city? Well, what part of Grand Forks?
What part of Grand Forks, right.
Right? So it's that kind of effect, right? Because of three-dimensional objects, clearly, the Orion Nebula. But it's very interesting.
It is. It reminds me of a story. I wish I could remember it. I'd go look it up. But they think they found, yes, our sun was clearly not born from a cloud by itself. So it would have had neighbors and sisters and brother stars, if you will. And they were excited because they may have found one of the siblings of the sun born from the same nebula, because it was a star that had the same metallicity and composition profile.
So what happened?
That's the last I heard of it. I didn't keep track of it, but I may go hunt for it now.
Yeah, that's right. That's been a big sort of search, was to look for the brothers and sisters of our sun. As you pointed out, you look for identical spectra.
Right.
And the other thing you think of, well, if we formed, 4.5 billion years ago, our sun formed and it had brothers and sisters into some type of maybe loose grouping of stars, an association, as we would say in astronomy,
right.
that those stars are on their own independent orbits around the center of the Milky Way, so they get spread out or dispersed along their orbits. So our brothers and sisters could, literally, some of them could be on the other side of the Milky Way from us today.
Right.
So it makes it impossible to find.
So it's kind of neat, though, that they think they found one at some point. And yeah, I'll go look that up. We
Yeah,
might have it on talk about it on another.
That'd be really
Sure.
cool. But if the other thing that's due to point out is, as we go through these different regions over time, these high density regions and low density regions and so on, they can disturb these things in the Oort cloud.
Right. Because it's tenuously bound by the sun's gravity. So
Yeah. And so you could have stuff that all of a sudden is inbound, like comets, and you could have a slew of them, not just a single comet, but a large collection of them heading our way.
our way.
And that's one of the things we always have to watch out for, is that kind of. In fact, that could be possible for, some heavy bombardment that happened in the past. Who knows, right?
Who knows?
People still look at that kind of stuff. Even some extinction events that occurred.
Could be because of that.
Yeah.
Yeah.
You never know. Now, if you want to learn more about this stuff, if you want to get involved in STEM-related field or otherwise, because we do need a lot of writers to describe science, to try to communicate that to the general public. And there's a great
Absolutely.
need for that, a real great need. And you just got to read stuff that has been published about different science, and you say, hey, that's not quite right. If you knew a little bit more about the science, maybe you would have found that or before you published it. But anyways, one of the places you can come to, of course, is the University of North Dakota. We have both courses online and on campus. And if you're around, please see Robert and I.
Absolutely. Come by and see
And
us.
it's never too late to learn, right, Robert?
Absolutely. I am taking classes myself. So
Einstein's a good example of that.
okay.
On his deathbed in the hospital, what do you find? All of his notebooks and pencils where he's writing stuff down. Right, it's almost right to the last moment he's working on stuff.
Right.
There
you go.
So that should be something we should all follow in life.
Indeed.
Lifelong learners.
Yep.
Now, speaking about Einstein, so we always leave you with a quote at the end. And by the way, our next podcast will be on March the 4th. And
Okay.
we will not have one on March the 11th. That's
Right.
spring break for us, so we're taking a 1-week break for that. But we will be here next week at the same time, 5 p.m. Central Standard Time on a Tuesday. But we always leave you with a quote. So today's quote is actually about gravitational lensing.
Okay.
Now, Einstein is given credit, always, right, for the writing down about this effect, this gravitational lensing effect that can be seen. In fact, he wrote an article in 1936 about this. And I'm going to read that, but then I'm going to add some history on the end of this.
Okay.
So here's the quote from Einstein. The title of his article was Lens-like Action of a Star by the Deviation of Light in the Gravitational Field. And I'll just read the first sentence or so, 2 sentences of this. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. And then he went on and described gravitational lensing.
Okay.
But I liked how he called it his little calculation.
His little calculations, folks. These aren't little calculations.
Which later on turns out to have a big implications. So but do you realize that the first hint of these gravitational lens-like thing that can happen from curved space-time was actually published in 1924 by a Russian physicist, Ores Kolovolsin. He published a paper in which he said that the halo of an object would produce this gravitational lensing of. Now, he didn't go into it and use those modern words, of course, but that's effectively what he said. In that sense, he beat Einstein by 12 years.
Nice.
To the punch. We don't really say about that. So it'd be nice, if like science historians would actually go back to the primary material and find out if somebody had been there before that.
Right.
But sometimes we forget about all those early investigations.
It's like relativity. People were aware of its impact and its consequences and things that were going on with it. It was just that Einstein was the first one to bring all these observations and everything together and work the math and say this has to be what's going on.
And there's even an argument there, right? The famous Hilbert for Hilbert space and quantum mechanics. As far as I know, he was a mathematician by training. He's the one that actually put general relativity together.
Right.
But before Einstein, because Einstein had given a presentation on it and found something wrong, and then went back to the drawing board and worked on it again.
Right.
And then made a presentation and went back. And by the time he got the final thing, Hilbert already beat him to it. And I think they asked Hilbert, "What do you think?" He said, "No, it's Einstein stuff. I just kind of helped with the math and did it." But he gave full credit to his. Nice person that he was, to Einstein.
That doesn't always happen, folks.
No, it doesn't. Sometimes science, because we're humans, can be a cutthroat business, right?
Right.
But not here at the University of North Dakota. We love everybody. So please join us if you want.
Come join us.
Anyways, thank you very much for listening today. If you really liked our podcast, please give us a thumbs up. And if you really, really liked it, please subscribe.
That's it.
Thank you. We'll see you next time.
We'll see you next week.